Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have a presentation from one of our students, Deaglán, who took our course ROS Basics in 5 days for Python. And this course includes the option to obtain a certificate by completing a real robot project, we call it, in which Deaglán applied what he learned in the course to a real robot in a project, and he's going to be showing it to us today. So, hello, Deaglán, how are you?
Hello, I'm fine. Yeah, thank you for having me here.
No, welcome to our channel, and I'm excited to see what you have done with your project. So,
Mhm.
whenever you want, you can start sharing your screen and get started with the presentation.
Okay, sure. Um, so can you already see it? I think now you should be able to see it.
Now I see it.
Okay.
Turtlebot wall following project.
Yeah, so I will put this here. So we can start with that.
Actually, I can only see.
Okay.
Oh no, now I'm good. Now I'm good. I see all
Okay,
the change now.
now you see the robot.
Yeah, I see the robot and the
Okay,
ROS
so
checked.
then let's make this bigger. Okay, so let's start the ROS launch. My ROS checked, the main launch. So it starts the 3 nodes. Now the robot will rotate, try to align himself with the wall.
Which wall?
The nearest one, so
The
it should
nearest
be
one.
the one on the right. Yeah.
So it's gonna face it and then go towards it.
Yeah. So now I have a little tolerance. That's why sometimes it's not completely vertical.
I don't think it matters.
It's just I will explain more about that later. Then it moved a little bit towards the wall, and then now it will actually start to follow it.
Oh, we got a little bit of an obstacle issue on top there. Let's see if it can handle it. Yeah, nice.
Okay, so and then I will also start the record autumn feedback.
Oh, nice.
Then it publishes the current distance, which it has already moved.
So that's the distance that the robot has moved total.
Yeah, exactly. And then it will do one lap, which is approximately 5.5 meters or 5. I'm not sure anymore what the exact number I put it.
Right. So you wrote a hard number for one lap.
Yeah, exactly. So then once it completed one lap, it will also publish the result, which doesn't happen yet, but it will complete one lap soon. So then the robot will stop, which is now.
Oh, nice.
Okay,
That's a lap of
so
5.5.
yeah, so it then, I made here a typo mistake. It should be record odom.
Oh, for the result, yeah.
Yeah. Let me see. So because it will actually publish it here.
Yeah, there it is.
Yeah, but it would also publish it here on the result.
But I don't think you're gonna get it anymore.
Yeah.
Unless you run it again.
Yeah.
That's fine. Don't worry.
Okay. So actually, I have also a video where I done it. Okay. So yeah. So this is finished. I will close the program.
Awesome.
And
Really clear.
prepare the presentation.
Nice, please.
Yeah. So you can see now, right?
Yes, I can see the presentation.
Okay. So yeah, it's the ROS Basic in 5 days with Python. So it's the Turtlebot, which follows the wall project. So yeah, like you already mentioned, it has basically 3 tasks, which is first, it has to find the nearest wall to navigate it.
Yeah.
Yeah. So this is done by a service server. Then it will follow the wall such that the wall is on the right side of the robot. Then it will publish the current odometry, and when the result is done, then it will publish the result. So this is done by an action server. Okay, so first, just to explain a little bit how it works, we can also then later go into the actual code. But basically what they did is I first make the robot stop, and then I check all the current laser values. And then I measure which one is the smallest. So this is the smallest distance. Then I try to rotate the robot until the front distance, which in my case is 360, is approximately equal to what I've measured before, the lowest beam. So it has a little bit of tolerance because since I'm, let's say, publish angular velocity, it has like, let's say, steps of rotation. It can happen that it over rotates.
And then you have to do a whole new one and it stays on forever.
Yeah, so that's why I have a tolerance that it has to be in some kind of range. Okay. Then when it has done this, then it drives until the distance to the front to the wall is approximately 0.3 meters, and then it stops. So it then again measures the distance which he has now to the wall, and then he tries to rotate to the left until the right laser 180 is approximately equal to what I've measured. So I think in the code it's 170, just that the robot rotates a little bit more to be a little bit more away from the wall to have a better starting position. And also here I have a tolerance, just that it can be approximately in range of the measurements. So then it returns a result, which is the wall found true. And after the result is true, then it can start following the wall. So I have also made a recording where we can see again what we have already seen before.
Right.
So yeah.
It hasn't found the wall, then it's gonna line up, and that's where we see that.
Yeah. So, and I have also here printed what the values are of the laser beams. What is the lowest laser value, and what my current, what basically at this point the front laser was. So then I have calculated the ray beams to rotate, so I know it's to the right. And then when he's at the wall, yeah, he's then turning to the left.
Right.
Yeah. And then he starts. Yeah. So then what's also doing is that, yeah, he follows the wall. So basically he checks the front laser and the right laser. And depending on that, I publish angular and linear velocity.
And linear.
Yeah.
So you don't leave it constant?
No.
Oh, nice.
Yeah. So yeah, what is with this is that you see it oscillates. Yeah, because it's basically just if and else. So if one value is like that, then it corrects to one side and then it does to the other. So I have like, I think 5 cases which happen, and then depending on this, I publish the velocity. So then I also publish the current move distance to the action server's feedback. And then also when the lab is done, the server result. We can also see this here now. So this is basically just the robot, which is then moving along the wall. So this is what we have seen also before. It publishes the current total distance.
I see. But
yeah.
I don't see the linear velocity change. You said it wasn't constant? The X?
No, I think the X is always the same.
It's always, yeah, okay, that's what I asked.
Yeah. Okay, yeah, sorry. And then I will actually go a little bit forward in this video. Okay, so I think here I had 6 meters for one lap, so it's more now, or even 6. Okay. So it stopped then also after one lap, and then here I have the result. Yeah, so it's in this record odom result. Yeah, and then it also closes the node.
Awesome.
So yeah, this is basically just one complete cycle. So it's again the same. He rotates.
Which is what we saw, right?
Yeah.
So why don't I ask you questions while we see this going on? You
Sure.
think that's all right? First of all,
or actually, can I finish? I have only a few slides more.
absolutely.
Yeah.
So I'm sorry, I thought you were done.
I think we have already seen the cycle. So I faced some problems. For example, sometimes it can happen that it collides with the wall. So I made an algorithm that now it will, let's say, collide with the wall, and it will try to get out of this. So it tried to go back and then turn again. So now it collides with the wall. It realizes that something is not good, that the front laser is infinite, and also an array of front laser is infinite too.
Right.
So I made a range. So and then it goes back, and then it can come out.
I love this. Let me tell you why. Because a lot of times students will leave the node that they're working on running, and the last one is a linear velocity. So I hear the poor robot going against the wall for like 5 minutes. I love that you did this.
Yeah. So actually, it took me a long time to finish this. Yeah. So I had a lot of testing until I finally managed to do it. Because now we will see again the robot collide with the wall. I mean, this can happen since sometimes, yeah, the velocities is not completely controlled, and then now
go back.
Yeah. So
and that's it, and then you
turn to the left.
All right.
So what he's printing is actually the seconds. So I made that he will drive 4 seconds back and then rotate around
and
8 seconds to the left.
Node again. That's so nice. That's really nice. Good job.
So then you can continue. Then also a problem which faces that, yeah, like I said before, sometimes it can happen that it does not completely align well with the wall. What would then happen is that he just would keep rotating for like forever. We can
because it was never gonna hit that one ray.
Yeah. So like this, then he will rotate forever. So I also corrected that. Okay, now I went one slide too fast. Okay, so here now we have the same issue, which is going to happen.
And it's going to detect it?
Yeah, so what I'm doing is that's why it's printing the seconds, which is rotating.
Right, because you know how long it should be rotating for.
Yeah, so when it goes for like 1 minute, so now then the robot will stop and then he will do the same algorithm again. So he will stop again, check again, which is the...
And then rotate the other way. Right.
Yeah.
But, and this is nice. I like it. Real nice. And then this time it does see it. Nice.
Yeah. And this is basically a loop, so it can go multiple times until it eventually works.
And you did this in conjunction with you told me you had a tolerance, right?
Yeah. So
does that mean like a range of values you're seeing, or are you looking at just one value?
I'm just looking at one value of laser beam, which is basically the 360 beam.
Right.
And
so then what's the threshold?
The threshold is like 0.06. So if the value, the lowest beam which he measured.
Oh, I see. If it's still a little in that range.
Yeah.
Okay, I see.
Okay, then what else have I done? First here. So one problem that can happen is that, for example, he detects an obstacle and thinks it's the wall. Yeah. So I haven't done an algorithm for this, but I think I would knew how to do it. So I think when you take actually a range of laser beam instead of just one, like I did now, then you can evaluate more data, and then you can
Right.
see that it will have peaks, and then you can see if it's an actual wall or if it's just one obstacle. So this is how I would do it, for example.
Yeah, yeah, exactly.
Then another issue is that, for example, when the laser dot is not good, for example, sunlight can reflect the
Oh,
laser, so you don't have clear data. So, I mean, that's basically a huge issue, which also happens sometimes in installation. For example, if you know HEVs, these mobile robots who do packaging,
right.
moving around, then a lot of time they have problems in the installation when the windows are not
Oh,
closed. And when you have like a huge sunlight, then the robot can also not evaluate good the laser data because you have different reflection, and sometimes we even have no values because the
so you
laser
get
beam
infinites
cannot.
or zeros?
You
Infinites,
will
I
get
assume.
infinites,
Yeah, yeah.
a lot of infinites, and yeah, I think this is a really hard one to actually correct.
Yeah.
I mean, it's the same if you
Like
would
close the
walk around
blinds.
in the dark. Yeah, I mean, maybe if you would have a map of the room, then you could, let's say, check where approximately at, and then let's say move in the dark according to your map. But it's quite risky to actually
There's
do
a lot
something
of
like
ways. Yeah, yeah. That's
that.
one. That's one. Another thing could be, look at the odometry and
Hmm.
check how you were going in the previous, I don't know, 5 seconds, and
Yeah,
based on that, like assume the wall is keeping straight. But oh, that's interesting. I hadn't noticed that the
yeah,
sunlight had an
yeah.
effect, and I really like that you showed the 24/7 capabilities of our lab because you
Hmm.
tried it both in the day at night.
Yeah,
I like that.
yeah. So yeah, because I was testing it, and then completely it turned like in circles and moved like in really strange way, and then I saw that it's because of the reflection.
Right. That's awesome. And that's one of
Yeah,
the advantages of testing things in the real environment. You cause
yeah, exactly, because it's not something you can test on the simulation.
right. Well, you could, but
So
that'd be a headache. I feel like.
yeah, so that's really, I mean, that's what happens a lot when you do testing just in theory, and then you go to a real installation, and then you have real life issues actually.
Right.
Uh, And so the last thing, yeah, so what could be improvements? I mean, yeah, you could have better controlling of the velocities. For example, a PID controller where you actually have dynamic velocities depending on the distance to the wall, so that it would go more in a line. But I think this is a lot of work to do, so that's why I haven't done it.
Right.
But something for a better project. And then, yeah, like I said before, use multiple laser beams to have a better data evaluation.
Awesome. That was
Yeah.
literally what I was gonna ask you. And
Yeah.
just to do the third part, what would you do with the would you do something different with the action server? Would you use this data? Do you think of another way that you could use the action server for something?
Yeah, so the odometry you can use to know where you actually are in the room. So you can also use this data to
Yeah.
locate yourself, and then also driving depending on where your actual position is.
That's yes, and I don't know if you know this, but the odometry always for wheel encoders for robots, it always will have a drift. So as you
Hmm.
go on, uh, the odometry will have a drift. So it'll have an error. So
Okay.
you can also match it with the scan and see how big that drift is. Yeah, nice. I just want to see if you thought of
Okay.
something.
Yeah.
So that's it.
Yeah, that's it.
That's amazing. Do you mind stop sharing your screen so we can
Sure.
look at each other for the end to hear?
Yeah.
Let me just fix this. Congratulations! It's a really really clear and easy project to understand.
Thank
I
you.
really liked how you answered my questions for me. I was going to ask you for improvements and for
Mhm.
challenges that you had. I really love the ways that you solved those challenges. I thought it
Mm-hmm.
was really creative. For example, I've never seen that if it crashes, notice it crashes, go back and try again. That's a
Mm-hmm.
great recovery behavior. It
Okay.
even
Yeah.
reminds me of autonomous navigation recovery behaviors. This is what if you I don't know if you continue with our courses and take
Mm-hmm.
autonomous navigation, you'll see that
Yeah.
the packages have recovery behaviors
Okay.
embedded into them. They're like plugins. You can make a plugin to say, hey, what happens if the robot gets lost? And
Mm-hmm.
I think this one could be a good like plugin to add there. I thought it was really really nice.
Okay.
And as
Yeah.
as well as the other one, the one that you know how much time you should be rotating for. So if it's past that, you can go back.
Mm-hmm.
That's a really creative way of solving it, and very different as well. It's really nice. Um,
Okay.
and yeah, and the improvements you said, I was gonna say,
Yeah.
you can do this. You can do the PID controller, which might will be a lot less work than you think. I believe it's
Okay.
just defining the error that you're gonna have, and then just using a simple like class for a controller. I can send you an email afterwards because it's not
Ah, sure.
it's
Sure.
a small thing, but it's a great improvement in
Okay.
behavior.
Yeah, that would be nice to see. Yeah.
Yeah, and then what you said about the obstacle detection, I agree. There's a bunch of filters that you can use to detect whether or not it's a wall or an obstacle. But
Mm-hmm.
overall, really really nice, Declan. I'm really impressed.
Okay. Thank you. Thanks a lot.
Thank you. And for everyone else that's watching, you've seen now two presentations for two different courses that we offer at the Construct in order to obtain a certificate. We believe is the last step in something like a online course that you should take in order to solidify the learning and the hard work you've put into it. So I invite everyone to do what Deaglán did here. And Deaglán, again, congratulations for a really well done project.
Okay. Thank you. Yeah, it's really great to have such a platform to practice ROS, and I think I will definitely check out more courses to keep continuing. And yeah, I think also what you mentioned that with these algorithms, I think there's still a lot to learn and to try out.
Nice. I'm really glad to hear that. I'm glad to hear that. So that's it for us, guys. So we'll see you again soon for our next presentation. And yeah, just keep pushing that ROS learning. See you later, guys. Bye bye.
Bye.
All right, Declan. That's